Our final speaker is Jim Barry, who is a senior scientist and chair of the research division at the Monterey Bay Aquarium Research Institute. Jim is a marine ecologist whose research focuses on determining the consequences of climate-related changes in ocean conditions for marine organisms and ecosystems. He spent much of his youth along the shores of Central California, where his curiosity and his love for nature and the ocean flourished. After high school, he stumbled into a summer job at McMurdo Station, Antarctica, and he did things such from cleaning bathrooms to organizing field equipment. And he had a few rare adventures where he actually was able to help scientists for a few days at a penguin colony, or he assisted with researchers on seal diving beneath the sea ice. And these experiences gave him a glimpse into the life of a scientist, and it fueled his pursuit to become one and led to college and a PhD. He can still remember one of his past scuba dives where he was under 6 feet of ice in Antarctica, and he recalls looking up towards the ice above him, and he was just thinking, how in the world did I ever get lucky enough to do this? So his piece of advice to anyone out there trying to pursue their dreams, their career, he says, you are capable of more than you think. Jim himself admits that he was pretty insecure and thought he wasn't smart enough to go to college, but that self-view was completely incorrect. So don't be afraid to participate in activities and put yourself out there. And with that, I will pass it over to our last speaker, Jim Barry.
Well, thanks, Madison, for the nice introduction. And it is kind of the way that my career was shaped. And I'll talk about that a little bit more in a couple minutes, but I'll go ahead and get started on this talk and give you a little background, and then I'll get into a little bit of my history. But let me share my screen. And now you should be seeing a couple whales in front of you. Is that correct?
Yes.
Okay, good.
Perfect.
So I'm Jim Barry, as we mentioned. From Monterey Bay Aquarium Research Institute, and I am no longer the research chair. I'm happy to say after 5 years, I stepped down. Someone else is doing it now, so I'm back to research. And I wanted to show this picture because this was an odd year when there was lots of productivity right near the shore at Mbari, and Mbari is right in the background there. These humpback whales were lunge feeding only 50 yards off the shore because all of these anchovies and sardines and krill were right there. So they get quite close to shore sometime, and we have them there as well. A tiny bit about Mbari. Mbari was started in 1987, a few years after David Packard from Hewlett-Packard Computers started the Monterey Bay Aquarium. And he wanted to bring together scientists, engineers, and marine operations people to form a partnership so that they could address important problems in ocean science that are limited by technology. So we develop new instruments, methods, techniques, and offer access to the ocean so that we can address some of these problems. We've got a couple research vessels like the one that you see. Let me get my pointer here really quickly. My laser pointer. So we've got the Western Flyer. I'll be talking about that a lot today. That's our main ship. But we operate a lot of undersea robots. Like one I'll talk a lot today is the ROV, or the remotely operated vehicle, which is tethered to the ship with power and fiber optic cables so that we control that robot from the ship, or others like these autonomous underwater vehicles that have propulsion and batteries in the back end and some payload. On this one, it's got cameras or bioacoustic sensors you can see in red here. Others, it might have even genomic sensors or samplers. On the left, there's Larry Bird, one of the engineers, developing and adding water samplers to this AUV so that the AUV can actually, using its software, find that special spot in the water column where either chlorophyll is really high or temperature is at a particular level, and he can and then collect samples right there for whatever analyses that are going on. Or even seafloor rovers or robots that sit on the bottom of the ocean 2 miles, 3 miles down for a year or more at a time, taking measurements occasionally, and then only coming up once every year to be serviced and have new batteries. So that's a little bit of background about what I get to do. I'm at this place where we define some of the interesting questions, and I'm a deep sea ecologist mainly. And the question is, how did I get such a cool job? And Madison alluded to this a little bit. And I was born right where the start of the Pony Express was for your history lesson, St. Joe, Missouri. And here's a little kid, I'm getting on a plane and leaving, and we're heading west with my family. And on the shores of California, we lived in the San Francisco Bay Area. I would crawl around on the rocks, dig up crabs, and just see what was there, learn to surf, and that became sort of my passion for a long time. And then as Maddie said, I was able to just kind of keep going to school and thought maybe if I keep studying this, I'll be lucky enough to get a job. With that experience right out of high school, sort of going out, getting a regular job in the Antarctic, which there really is no such thing, and then helping some scientists, which I thought they had great jobs. So in the end, I was lucky enough and studied hard enough to go ahead and get a job, diving under the ice. In this case, this is a special shark in the Gulf of California. So that was kind of how I got to where I am. And I've now been at MBARI for over 30 years. So now let's get on to the talk. First of all, I thought, since we're talking about the deep sea, a lot of people don't know what it is, don't really care about the deep sea. So why should we? But what is the deep sea? Well, first of all, it is by far the biggest livable space on Earth. This planet is about 60% covered by waters that are deeper than 200 meters, and roughly 200 meters is considered, greater than 200 meters is considered deep sea. But about 95% of the ocean's volume is greater than 200 meters, and that's the biggest space on Earth. So it's divided into various zones, and I'll quickly talk about some of these. Surface waters, not the deep sea, is where all the action occurs that feeds the deep sea. That's where light penetrates the ocean enough for phytoplankton to grow. Phytoplankton are the base of the food chain for nearly all of the deep sea. And there's a lot of animals that come up to feed in surface waters during the night. During the daytime, they hide from predators. Then you get down to, say, about 1,000 meters or a few thousand feet. This is the twilight zone where there's a little bit of light, and there are all kinds of animals here, predators and prey. And there are a lot of predators that are looking up to see if they can see the silhouette of those animals that are above them with that weak light that's coming down. Here's the Dositicus, the Humboldt squid that Ileana mentioned a little while ago. It's common there. The midnight and abyssal zones are much deeper. I'll be talking about these a little bit today. All kinds of predators down here, things like this fang tooth with these enormous teeth, and you'd think, gosh, that's the scariest thing down there. But I'll have to say, it's not always the scariest thing. Here's another squid. This one's called Gonatus, a small squid. It's about 6 inches long or so, and it's now eating one of these fang tooth fishes. So you've got to be watching out no matter where you are in the deep waters. And then the deep sea trenches up to 7 miles down in the Marianas Trench, and I'm not going to be talking about those today. But we have to understand where this food is coming from. I mentioned that all of the phytoplankton that produce food then sinks toward the deep sea, called marine snow. And oops, excuse me, I knocked over my microphone. And we've been talking about poop a lot today, and poop is one big component of what sinks toward the deep sea. Dead carcasses of little tiny animals, or all the way up to the size of a whale, are things that sink toward the deep sea. And as they sink, they're being recycled. Things are eating them, things are recycling them, and their carbon value or their food value diminishes as you go down. And about every 1,000 meters or a few thousand feet that you go, about 90% of that material is used up. So by the time you get to the very deep sea, it's a very food poor environment. And it also matters where you are on Earth. Off our coastline here in California, it's a very rich ocean. There's a lot of material exported toward the deep sea. But if you live in one of the sort of ocean deserts, the mid-ocean gyres, there's not so much productivity on the surface waters. And because of that, there's much less food in the deep sea as well. Okay, that's my quick background about the deep sea, but I want to give you some sense of what does it look like when you're down there. So I mentioned we use this ROV, the Doc Ricketts, and this is in the middle of our ship. And here's a quick video multiplied by about a factor of 10 going down. It's launched through these barn doors in the middle of the ship. You get down into the surface waters there, you can just barely see the ship. Surface waters in the summer are green. As you get deeper down, this is that marine snow. Sometimes there are layers of lots of little myctophid fishes or other fishes. These are called flashlight fishes. Little jellies are swimming by, and I'm kind of zipping down. Now we're at, this is about 1,200 meters deep, a few thousand feet again, at the top of a seamount we call Sur Ridge that I'll be talking about a little bit later. And so that's kind of what it looks like. This marine snow is constantly coming down. And today, with that background, I'm now going to tell you 3 little short stories. One of them is about these coral gardens at Sur Ridge. You just saw a glimpse of them. And the second one is about the octopus's garden at the base of something called Davidson Seamount off of California. This is an extinct volcano. It's a submarine volcano. And down at 3,000 meters depth, 2 miles deep, there's some octopus's gardens that I'll talk about, and then some mystery holes I'll finish up with a very quick story. All of these depend upon our using this ROV Doc Ricketts, where we sit in the control room of the ship. The pilots drive the ROV, and then the scientists are over here controlling the cameras and asking the pilots to collect this or look at that. And together we are able to get down to the bottom, even a couple miles deep, and do research. Okay, now on to the deep sea coral garden at Sur Ridge. Just to give you an idea, this is Monterey Bay. MBARI is right in the middle there at the head of Monterey Submarine Canyon, and we're going to talk now about Sur Ridge. So we have established something called the Deep Sea Coral Observatory at Sur Ridge. Well, why do we do that? We're interested in trying to understand what factors are influencing the lives and deaths of deep sea corals and sponges that live in these rich environments. Deep sea corals are important places. They're found all over the world, including right off of Sitka. And if you get into deep water, you'll find some of these corals. They're different from shallow water corals. Shallow water corals have symbiotic algae in them that photosynthesize, and the coral itself actually gets much of its nutrition from the photosynthetic algae. There's no light where these corals live, and they depend upon this rain of organic debris that you can see just drifting by this candelabra coral here. So we have a number of sensors here, moorings that capture the amount of food coming down in little funnel traps, other moorings that tell us the currents, the oxygen concentration, the pH, other sensors right on the bottom to measure currents, and even time-lapse cameras. And I work with lots of partners here in the Monterey Bay National Marine Sanctuary about this. A little bit more about deep sea corals. Many people call them the old growth forests of the deep sea. And the reason they're called that is that they're very much like the forests we see on land, where here's a big sequoia or redwood tree cut in half compared to a little tiny, or not that big, about a ½ inch across cross section of a deep sea coral, one of these bamboo corals. And that 1/2 inch across is 250 years old using some radiometric aging methods. So they grow very slowly. Here's some pictures of some skeletons that we've collected with the ROV. And we try to collect skeletons if we can, rather than live animals, because we don't want to damage them. But these skeletons, even that height, take several centuries or even longer to reach just a few feet tall. And some of these corals reach 2 to 3 meters tall, say 12 feet tall at times. Now, I mentioned, here's just a nice video. I hope you can see this with the little particles of marine snow running by. And these corals, this image here is probably about 2 inches, 3 inches across. You can see this is a colony of organisms that have specialized polyps like these, just like little sea anemones. And these polyps are capturing particles. Here's one that's probably captured particles. And they eat organic debris that's coming by, or try to capture little shrimps and other little animals that are floating by while they're living, and then slowly they grow. And they're important to a variety of animals around them, including fishes. There are many deep sea fisheries that depend upon coral habitats for their nutrition. And so they're kind of specialized environment that the sanctuary in particular is interested in protecting. Now, what is it that regulates their lives? Are they most susceptible to just flow and food that's coming by, or could predation be a significant threat to them? And there are some important predators there, sea slugs we see up on top of them, or sea stars. You can see this coral colony has had some damage, presumably due to these sea stars. And in other cases, like this large coral here that's about 6 feet tall, it has a veil of sweeper tentacles, and these tentacles are loaded with little stinging cells. And we think that functions very effectively in keeping predators from having access to the feeding portion of the colony. And just as an example of what the predators can do, we stumbled upon a coral colony that had fallen over. It was on a little rock that sort of rolled over in the current in August of 2017. And you can see it's already been consumed in part by a variety of sea stars and sea slugs. And we came back and visited it just 4 months later, and you can see by that time it was nearly gone. And by even less than a year later, it's totally denuded, except for one little sea star in the corner here. And so if you think about how long it took for this colony to grow, probably 200 to 500 years, it was all gone in less than a year. So these predators have the capacity to wipe out a colony. And that's what we're concerned with. Can they do that? Or is something else going on? To carry on a little bit with this predation idea, we did a little experiment in the deep sea, which is not easy to do. We took some branches of the feeding branches of a coral, a couple different species, set them on the bottom, some of the stinging branches, set them on the bottom, and just some of the skeletons that we found, and then collected a few sea stars and put it on each one, and positioned a camera nearby, and then turned the camera on, and then followed it for about 4 hours just to see what the behavior of these sea stars would be. And this is now sped up by a factor of 20 or 30, but you can see they're kind of moving around, especially from this middle area, which is this stinging branch area. And we came back and watched them once in a while with the ROV. But if you sum up what they did, here's a graph of the stinging cells, the feeding branches of two different types, or the skeleton, and how many hours it took for the sea stars to leave. They pretty much, it took them less than an hour to get off of the feeding tentacle, or the stinging tentacles, pardon me. And that's quick for a sea star. They're not very fast in the deep sea. And on the feeding branches, the sea stars stayed much longer. And in some cases, they everted their stomach and started feeding on the corals, just as we thought they might. So it looks like the stinging tentacles have the capacity to deter these predators to some extent. Now, to carry on with that predation story a little bit, maybe it's not predation on the adults that's really important. Maybe it's predation on the little tiny colonies. And we have a deep sea camera here. It's basically a regular old SLR camera you might buy in a big housing with a big float to get it back and some strobes. And we put it down next to this large rock. This is the image it saw. And it took a picture of that every hour for a year. We brought this back last March. And so here is I've compressed those 8,000 or so images into 1 minute, and I won't show it all, but I do want to show you a couple spots here. In this top circle, you can see a little baby bubblegum coral, this pink coral. That's a little baby bubblegum coral colony. And here's a sea star. And when I first start this, you're going to see all kinds of activity, but that sea star is going to run over and consume that coral. And so there it is up on top of it. And so it is on there for a little while, and then it departs, and you can see now the coral's been denuded and killed. But there's all kinds of activity going on. It's really frenetic, and in part, the currents are so strong, the corals are moving back and forth, and even the whole frame of the camera moves a little bit, which makes it hard to figure out. But my postdocs and another intern are looking at this video now to calculate what kind of species are coming and going, and how are the feeding of the corals changing with either daytime or currents or tides. And I'll stop it now, but I'll just give you one glimpse of some of these results. Here's one of the branches of the bubblegum coral with its feeding polyps closed. And then in the middle, they're just partially open here, and on the right, they're fully open. You can see it looks very fuzzy. And if you count up through the year, when did we see it feeding? In green, it shows that between July and November, that's when most of the feeding occurs. And in the wintertime, they sort of close up their colony and they don't really open up, perhaps because it's risky to be out there feeding if there are predators about. And this orange line is one of the traps that traps the organic debris coming down. That's an estimate of how much food there is. And it's a little bit of a rough relationship, but there's more food in the summer and fall after the plankton blooms in spring and summer, and that material slowly makes it to the bottom. So we're learning about what regulates these animals and so we're learning about predation, we're learning about the influence of food on their dynamics, and we're doing various other things to try and understand reproduction, coral health, and whatever. But that's just a glimpse of what we're doing in that system. Now I'm going to move on to story number 2, the octopus's garden. And this is a story that we're working on right now quite a bit. And the octopus's garden is at the base of Davidson Seamount. And there's a program that NOAA, the National Oceanic and Atmospheric Administration, runs something called their Ocean Exploration Program. And they asked us, our ship's going to be out here this year. Where should we dive in your area? And one of our experts on this volcano, underwater volcano, said, you should go look at the foothills down here. We don't know much about them, but they look very interesting. So they dove there with an ROV and a sub, and they found an octopus's garden, or what they call the octopus's garden, of aggregations of octopuses breeding together. And these are all females sitting here. And I don't know if you can see the shimmering water here, but they are breeding in geothermal springs at 2 miles deep. And that shimmer is due to the warm water emanating from the seabed. And they're sitting in that water. Oh, and just as a kind of a scale, these octopuses are about the size of a grapefruit. So a little bit about octopuses. This octopus also is found at usually when you see it, it's found at some sort of food fall, like this whale that was found on that same cruise. Lots of these octopuses, as well as a variety of other scavengers. And they're either scavengers that are feeding on the carcass, or others think they're just feeding on little animals, like little crustaceans that feed on this carcass. So they're mainly predators. And the question is, what are they doing here? And on the left here, this is a male in real time for a moment coming down, trying to find a female to mate with. Here's a female, and she repels him. And now I'm speeding up the video to about 10 times normal speed, and you'll see him kind of crawling around. And what you can't see in this video is down below this rock, there are about 50 more females sitting there that he may sense. And so this is a shot of some of those females on their nest. They just sit there, and there are things like these large anemones and other shrimps here. And when the eggs are hatched, these anemones would love, we've seen them capture some of the babies, like this little paralarva that's hatched. We see females and males coming in, reproductive or incubation of the eggs. You can see these have eggs or eyes, and hatching, and then these animals breed once and then die. So the question is, what are they doing down there? Are they there for the food? Are they there for the heat? Is it there because of reproduction? And what we'd like to know is there a large population here? Is it just an isolated group? And one thing about the deep sea that you may not recognize is when you're down there with an ROV or in a submersible, you can only see what is directly in front of you. So imagine that one of your friends says, let's go for a hike, and I've got a helicopter. We're going to go to a new spot. And they take you on a moonless, dark night, land you on the middle of a hillside and give you a flashlight. You can see what's in front of you, but you have no landscape view. So how do we get that for the deep sea? Well, we have what we call an ultra resolution imaging system that is mounted to the bottom of the ROV. One of our engineers developed this, and this is sort of looking at the bottom. It has some very sophisticated sensors. It has a multi-beam bathymetry system, so it uses an acoustic mapping system that gives us 5-centimeter resolution of the bottom. It also has a LiDAR or laser-based mapping system that gives us a 1-centimeter measure of the bottom. And we also have dual stereo camera images at the same time. The octopus's garden is on a little knoll at the base here. It's only about 100 meters, 200 meters, or sorry, about 1 kilometer long. And from that mapping system, here is the bathymetry map we were able to make. This area is about the size of 3 or 4 football fields, to give you a scale. The lighter colors, or the oranger colors, are shallower. The bluer colors are a little deeper. It's only a couple 100 meters from the top to the bottom, but you can see some cracks and crevices. And if you take this stereo camera images and paste them all together, now this is a mosaic of more than 10,000 images. And it doesn't look like much here. You can see that kind of mowed the lawn back and forth to get this. And you can see dark areas where the springs are. But what we've also done, when you zoom in here, you can see a lot. So here's a shot. If you zoom in, you can see in this case, there are about 200 octopuses there. And if you zoom in a little more, you can see individual octopuses crawling around. And that's just kind of the close-up. But if we want to understand the distribution of these octopuses across the whole area, we've used some image analysis software, and I've marked the locations of over 7,000 nests in pink here. And you can see they're sort of distributed all over, but they're very closely aligned with those cracks and crevices where these hydrothermal springs are located. And I mentioned, what the heck are they doing breeding in warm springs? Is it there's more food there? Are they protected by predation because there are many of them in a group? Do they have some breeding advantage because there are more mates there that they can find? Or is it warm water that's moving their metabolism a little faster so that gives them the ability to develop more quickly? And that's what, or is it some sort of spa day? You know, well, we all like to kind of sit in a hot tub, and maybe there's something going on with the octopuses we just don't know. I suspect that's not the case, and we didn't pursue that much, but I am going to tell you what we have done to try and understand what they're doing there. And so we had a field program where we went out and measured temperatures, and we put temperature loggers and oxygen loggers as well in some of these, some very close to nests, some not in nests. And we took repeated visits and revisited nests that we had mapped out. And then we would try to figure out what the rate of these developing larvae were, or how long the females were in the area. So we would go in, and when octopuses first lay their eggs, they're pretty clear, and we would follow them or rate which stage they're in. Octopuses all have a number of stages, about 20, that they go through in development. And you can know that if you're at stage 10, you're halfway through the development or something like that. So we would rate the stage of development. We would measure the temperature by nudging the female aside a little bit and measure conditions. And we would also try to identify the female by some scars here. So here's March 2020 and December 2020, and you can see that same scar. This is the same female. And just to cut to the chase on conditions, in the eggs, we found the temperature was about 5 degrees centigrade or 41 degrees Fahrenheit, and ranged from a little lower to a little higher, but never super hot. You never found them to be hot enough to cook the eggs. And the ambient temperatures are very cold, 1.6 degrees centigrade or about 35 Fahrenheit. So they're a little bit warmer, or to quite a bit warmer in these nests. Now, could that affect their development? And that takes a little bit of information from the literature. So if we take a look at temperature on the x-axis versus how long it took for the incubation to finally lead to hatching, for all these different species, one dot is one species of octopus living from the tropics to colder waters, what we find is this nice relationship that we can then predict for any temperature what we would expect the brood period to be. And usually when you get outside the range of your data, then you're extrapolating and there's very little confidence in it. But there was, so this prediction for about 3.5 degrees would be pretty long. So that's previous studies. But Bruce Robeson, a colleague of mine here, several years ago found an octopus in the deep sea laying eggs. And so he started watching how long it took Octomom to hatch her eggs at 38 degrees. It ended up taking just over 4 years, 1,590 days. And this is the longest incubation period of any animal known on Earth. And so we have an octopus, moose octopus that I mentioned over here, that lives at even colder temperatures. And if you use the temperature of 35 degrees and this relationship, you would predict 4,483 days, or over 12 years for this animal to hatch its eggs. Now that seems incredibly long. And is that what's really happening? Or we measured 41 degrees in these nests. Will their incubation period match what we see for the nests? So we went about using the data that we, from the repeat visits, to try and assess that. So that, are they taking this shortcut basically by getting this metabolic boost from that warm hot spring? And so just to recap the prediction, 35 degrees, you'd expect 12 years. 41 degrees, you'd expect about 1.5 years or 600 days. And what did we find? Well, we found that the actual brood period was just what you would expect for 5.1 degrees centigrade or 41 Fahrenheit, about 600 days. And the female residence time, how long they stuck around on the nest, was about the same as well. So it really looks like they're using that warm water to get a metabolic boost to accelerate development of their larvae and sort of reduce it by about 90% by breeding in those warmer waters. Well, what's the big deal? Why should you do that? Well, there's a benefit to that. If you, let's say you lay 100 eggs, and they usually lay about 100 eggs, how many of those are going to hatch? There will be some mortality. Some may be dying from damage, bacterial infections, predation, who knows what. But let's assume that's 5% per year. If you take 12 years, you're only going to have about 6% left by the time you get through the incubation period. If you can accelerate that development, and as long as there's no additional damage, you can hatch maybe more than 10 times as much of your brood. So there's an obvious fitness or reproductive advantage to doing this. Now, so the advantages are just what I mentioned. You get higher hatching success and maybe a reduced risk of female death, but there are risks. If if it does get too hot, you're going to cook your larvae or cook your eggs. And there's another observation of a breeding aggregation like this off Costa Rica by Ann Hartwell and colleagues, and they found that none of the eggs were developing, and it could be because they bred in water that was too warm, and they thought the population was making a mistake by breeding there. And finally, on this story, the deep sea heat sources, they might benefit other people around hydrothermal vents that you've seen, these magnificent animals, or other warm springs like those that I've described here. And there's one paper that says that deep sea skates will lay their eggs in warm water near hydrothermal vents, presumably to have that metabolic boost and the benefit of the rapid larval development. So we've learned a lot about this species, and it's been pretty interesting to try and figure this out, and that's an ongoing story. During that last cruise, one of the things that we did is try to go look for more. This is the octopus garden here, the lower right of this really odd looking map with different colors. We decided to go on an exploration dive and look for more octopus gardens. And we led to discovering some mystery holes 2 miles deep. So right here is some of the video sped up by about a factor of 10, where you're going along at 2 miles below, and those laser dots you can see are about a foot apart. And what you come upon once in a while are holes on the bottom, like these right here. And when you find some, you tend to find more. And this is kind of what they look like. And it looks like an anchor hit the bottom. And this is 2 miles down. Nobody anchors in 2 miles depth. And so if there was something here that hit the bottom, where did it go? So it became sort of a question, and we actually had internet on the boat. So I started searching the science literature and found that these pits we think are made by marine mammals feeding at the bottom. And the two that come to mind are Cuvier's beaked whale that gets about 25 feet long. It feeds on deep sea squids and fishes, and it sort of fits not just off Monterey here, but it's been seen off Alaska, off in the Arctic, in the Mediterranean, this same characteristic seafloor scar. And so we think their beaks are actually smashing into the bottom as they capture some sort of prey, like some of the squids that Ileana talked to us about earlier, or some of the other cephalopods or fishes that are ranging around the bottom there. But it's a curious observation that we found just recently. Now, to finish up, we do hear these animals as well. MBARI operates what's called the Mars Observatory, a cable that comes out and goes out about 60 kilometers offshore to 900 meters depth. And at that location at the bottom, we have power, we can plug into it and get power and internet. And one of the items that's plugged in there is a listening device called a hydrophone. And we hear all kinds of noise from all over the place, ships going by, marine mammals all the time. And I would play Cuvier's beaked whale, but it's really hard to hear. It's just a little click. But I do have a couple others just to finish up this talk to see if you can tell me what they are. So here's the first one. I hope you can hear them. That's a humpback feeding somewhere in Monterey Bay. I'm actually not sure where the video came from. And then your last quiz for the day. Orcas. It's so exciting. And so one thing that you can do, we actually have at MBARI's website, I don't have the link here, but there is a live link to the hydrophone in the ocean, and you can listen to it anytime you want. Sometimes all you hear is background noise. Sometimes you hear lots of singing from humpbacks or other things. So check it out at MBARI's website. Now, just to get back to the kind of the big picture, I mentioned not that many people care about the deep sea. Well, who does care about the deep sea? I mentioned that it's one of the biggest spaces on Earth, but I didn't really talk about why it's important to us. And we get all kinds of freebies, or what's called ecosystem services, from the deep sea. Foremost, climate stability. Without the ocean and that large heat sink that is the ocean, our climate would be far warmer, far colder. It wouldn't be habitable. Food. There are a number of deep sea fisheries. Many of them have been depleted lately, and that's very important to us. But the other element of our food that people don't realize at all is the deep sea does most of the what's called remineralization of organic debris. So when we turn fish back into nutrients, that happens as microbes and organisms consume that material and metabolize it, regenerating nutrients like nitrate, phosphate, that then are, by deep sea currents and other currents, are re-injected into the upper layers of the ocean, where they fuel additional productivity for all of the other fisheries that we depend upon. So it's very important. Energy and minerals, there's all kinds of things going on. And right now, deep sea mining has come up as something that's really starting to develop for the future. Biodiversity, there's a whole field that's called natural products chemistry, where scientists go out and collect odd organisms, plants, animals, whatever, from forests or jungles or deserts or the deep sea, and then look for odd chemicals that might have some bioactive function, like antimicrobial, anti-cancer, anti-pain, whatever it might be. And that's something that there are a number of deep sea species, hundreds of deep sea species that have been found that way. And inspiration, the vastness and mystery of the deep sea is something that many of us think about and appreciate. So who cares? We all care. Even if we don't think about the deep sea, we all care about our own lives. We care that we're going to be able to keep fisheries going, have stable climate, et cetera, and the deep sea plays a big part in that. So I want to thank you all for inviting me here today, and I have many people to thank at MBARI and beyond that I won't go into today, but I'd be happy to answer questions if you have some. So thanks a lot. And I'll stop sharing here. I can figure it out.
Thank you, Jim. That was great. And I really appreciate connecting it back to the big picture. Also, I think when we decided to do predator and prey as the theme, I don't think many of us were thinking about how maybe sea stars were at the top of the list. I mean, wiping out over 200 years of growth in like less than a week, like that's horror flick material. That's crazy.
Yes.
Okay, we have tons of questions and some time to answer them. Let's see what we got here. I was so intrigued with the talk, I forgot that I have a job to do. Question from one of our watch parties in Sitka. What do you do if the underwater technology breaks or malfunctions? Can you retrieve them?
That's a great question, and that is something that is really challenging because it always breaks and it always malfunctions, and especially when you're first developing a new sensor, it's very difficult to get it in the lab, or we have a test tank here to put things in the test tank. You develop some new gear and you think, okay, we've got it all bugged, we've gotten all the bugs out, let's put it in the ocean. And invariably something happens. And one of the great things that we learned early is that we have to have access so that we can go out and iterate. We have to be able to put it in the water, test it, bring it back, refine it. And sometimes that takes even decades at times. This mapping system that I showed you, that developed well over a decade. So, and there are all kinds of problems. And sometimes we even dealing with the high pressures there, we have canisters that we put things in. And if they leak a little bit, sometimes they'll leak and batteries get wet and they can actually explode. And we had one come up and it had exploded underwater. We weren't sure why it wasn't working, but we found out. So it does happen, and we just try to do our best to get the engineering right the first time, which you won't get it perfect, but you might get it close, and then refine.
Yeah, it keeps you on your toes, right? Because you never know what's going to happen when you get it out there.
That's right.
Good question. All right. Have you found any new species of fish or anything in general while using robots in the deep sea?
Excellent question. We find new species all the time. In fact, right behind me, here's this octopus garden. We found a new worm in this, I think. We found new fishes. We found, usually you can find new species of worms because there's so little known about the deep sea. Samples that you pick up, oftentimes it's hard to identify what animal are we looking at, because if you're in the intertidal here, or if you're fishing, you can look at your fish guide or your intertidal guide and figure out just about any organism that you find. But those guides don't exist for the deep sea. So you're often calling up taxonomists that work for the Smithsonian or other experts that all they do is look at sea stars and do the taxonomy of sea stars. So you're relying on those, and at times we'll send a photo or send a specimen and ask, and they'll say, oh, this is a new one. And there's a long line of species that we've discovered that need taxonomists to name them for us. And I've named a couple new clams that we discovered in the deep sea here. So yes, we do find them all the time.
That's so cool. And it makes me jealous. I feel like a lot of researchers get jealous of the olden days where you'd go out and just discover something new, but it seems like the deep sea is still that place that you can just go out and discover something new. Very cool.
Mhm.
Okay, we have a question that was voted pretty high. Could climate change improve conditions for the small octopus?
That's a really interesting question. And you might think that, oh, the deep sea is immune to climate change, but that's absolutely untrue. And in fact, climate change, in terms of the percentage change of conditions in the deep sea, in some cases is moving faster than it is on the surface. Normally in the deep sea, the temperature just does not change. It's really stable. There's a little bit of change through the year, but it's nothing like the changes in shallow water. And so the animals that live there, in some cases, may be adapted to a very narrow range of temperature. And if you warm it up just a little bit, for example, fishes in the Antarctic, you warm them up just 4 degrees and they can't take it, they die. So the question is, what is the capacity of things like octopuses or other animals in the deep sea for what are fairly modest changes in temperature in the future? One thing that happens when you warm up cold-blooded organisms, their metabolic rates go up. So what happens when their metabolic rates go up? Well, you use more oxygen because you need it. You're running your tissues faster. You need more food. It may help in octopuses. I think it really helps for their development for deep sea octopuses. But in other cases, if they live in a food poor area and they need more food, but there isn't more food, because with global warming, you also get reduced productivity in the surface water. So that rain of organic debris diminishes a little bit. So there's less food, but you have more need for food. And so we don't know how it's going to play out completely, but my guess would be it's going to be problematic for animals in the deep sea, just like it is in shallow water. And the way I like to think about it is, what do you spend your money on? I get a paycheck, I pay the rent, I pay the utilities, and I buy food I need, and then the rest of it goes to my son's education and vacations, let's say. Well, if the cost of living goes up because now I need more energy because my metabolism is higher, excuse me, bubbling, then something has to go. If there's less food, or let's say even the same food, the cost of living goes up. What goes for animals? Well, it's reproduction and growth that you're going to lose on. So you may be reproducing less and growing less. And that's how it may play out.
That's a great analogy. Awesome. Okay, let's see. Let's see. Sorry, I realized maybe I should put my glasses on. All right. Does marine snow come from the surface, the bottom, or both?
The marine, well, that's a very sophisticated question, because marine snow is really, we think of it as that organic debris, that snow you saw in the water. And when you're in an RO or looking at an ROV, or you're in a submersible, it really looks exactly like a snowstorm when you're flying through it. It is all of the debris that comes from everything that lives at the surface, and it sinks toward the bottom and it lands on the bottom. And then currents can resuspend it. So even though it originated at the surface, it can actually be resuspended from the bottom. And so it comes from both places. And that's the food for the deep sea, except for places like hydrothermal vents, where there is some growth that doesn't have to do with surface productivity.
Awesome. Great question. All right. 5 people are interested to know, why are sea slugs and sea stars feeding on the deep sea coral so much more than they used to? Are they lacking other food sources?
I mean, it's a good question, but I think it takes, maybe I need to explain a little bit more. I don't know that they're feeding more than they used to. So the corals are there and they don't want to be eaten, obviously. And our question is, where's the bottleneck for populations of corals? Is it, if you can get to be a foot tall, does that mean, okay, I've made it now largely, as long as I can keep sea stars off me? And we don't know that, but we do know, I showed you that time-lapse video of that little tiny baby coral sitting there trying to make a living, and then boom, gets nailed by a sea star. We've seen that elsewhere as well. It happens a lot. And I think one of the real difficulties for some of these deep sea corals is not later in life when they're getting really big. It's when they're this big. It's when a sea star can come over you and just dominate you and just wipe you out. But there's another rule in deep sea coral communities, and I think that is, To fall over is to die. You know, if a coral colony, you saw that one, and that's not the only one we've seen that's fallen over, but in every case, they're denuded when they fall over. So you got to stay upright. And they fall over sometimes because they land on the wrong kind of rock. You know how there's some really hard, well solidified rock, and then you go and there's some kind of friable sandstone along whatever shore you've been on. Well, if you're a coral that has to glue itself to the rock and then it's going to stay there for several centuries, you better choose the right rock, because if you choose one that's going to erode out from under you, you're going to fall over. And so we see that happening too.
Oh man, rough life for corals for sure.
It's slow motion, but it's rough.
Yeah. Well, that is all the time we have for questions. We have so many more up there, so I appreciate everyone out there that send in their questions. And thank you so much, Jim, for such a great talk.